All right, so with chapter 17, we're going to continue to look at equilibrium a little bit, but we're going to look at some different factors that are going to affect equilibrium. And it's so far we've kind of seen just equilibrium in general in terms of Le Chatelier's principle. We've seen it with respect to acids and bases, and we're going to continue to, for the most part at least, focus on it in terms of acids and bases. But we're just going to have, as the title would suggest, sort of extra pieces with it. Oops, that's not good. And so far, we look at this reaction. So this is going to be the dissociation of acetic acid. So we can see that hydrogen from acetic acid is going to combine with water to give us the hydronium ion, and it'll free up the acetate as well. But since H2CH3O2, this acetic acid, since that's a weak acid, that's why we have the equilibrium we have here. And so far, we've kind of just thought about this in terms of taking this acetic acid and just dissolving it in pure water. But with the common ion effect, what we're going to see is in some cases, we may be taking this acetic acid and dissolving it in a solution that is already containing maybe some of this acetate ion. And if we already have some of that present, that's going to affect how much of this solution can actually dissociate. So if we think about it in a different way, if we have this reaction, we did just, let's say, maybe take acetic acid and place it in water, we're going to allow it to reach that equilibrium where a small amount of it is going to dissociate into the hydrogen ion and the acetate. But now if we took something like sodium acetate and dissolve that into this solution, it's going to increase the amount of acetate ions. So it's going to shift the reaction to the left. And what we're going to see with this common ion effect is just when we have a common ion in the presence of a weak acid or weak base, a weak electrolyte really is just another term for that. Weak acid, weak base, because they're not going to fully dissociate. They'll only give us some ions like the weak electrolytes will. But if we then take a strong electrolyte that contains one of those ions, like I was saying with sodium acetate, that's going to decrease the amount that weak electrolyte is actually going to dissociate. It's going to decrease the amount of ionization we have. And if we look at an example like we have here, we want to calculate the fluoride ion concentration and then determine the pH of a solution that's going to be 0.20 molar with respect to hydrofluoric acid, and it's going to be 0.10 molar with respect to the hydrogen or hydrochloric acid. So we're going to have both of these acids present at these concentrations, and we want to think about what the fluoride ion concentration is going to be, so what's F minus, and then ultimately what the pH of the solution is going to be as well. And if we look at it here, Ka for HF is going to be 6.8 times 10 to the negative fourth, and then hydrochloric acid is just going to be a strong acid, so it's going to fully dissociate H plus and then Cl minus. So when we think about what's going to occur here, when we're looking at the fluoride ion concentration, when we think about the dissociation of HF, we're going to wind up with H plus and F minus. But with it, since we already have HCl as well, we're not going to have zero of this hydronium ion. We're already going to have some of that present, and it's going to be the concentration of the strong acid. So since HCl is going to fully dissociate, if that had a concentration of 0.1, we're going to see the H3O plus is going to have an initial concentration of 0.1. So if we look here, we've just got our ice table. HF, for the reactant on the left, we're going to skip water since it's a pure liquid. And then with the H3O plus, could also just be H plus. Again, those would be the same thing. And that fluoride ion, if we look at the initial concentrations, 0.2, because that was just what we had in the previous question for that hydrofluoric acid. Again, the 0.1 here is coming from the HCl. So that was just the concentration of HCl. But we don't have any of that fluoride ion present initially, because any of that fluoride ion is just going to come from this HF. But once we have this, we can kind of approach it in the same way. We're going to use up some amount of the hydrofluoric acid. And then since we've got a one-to-one stoichiometric relationship here between all of these coefficients, if this decreases by negative x, our products are just going to have to increase by positive x. And then since the fluoride ion had nothing to begin with, the equilibrium concentration is just going to be X. And then for the other two substances, since they did have something to begin with, we're going to have 0.2 minus X for the hydrofluoric acid, 0.1 plus X for the hydronium ion. But because we saw with the previous slide, the Ka here is going to be pretty small, 10 to the negative fourth, so not the smallest we've seen, but still going to be a reactant-favored reaction. So what we're going to be able to do is essentially just ignore the X for these two substances and set it equal to 0.2 and 0.1 for the equilibrium concentrations there. So when we go through and solve for it, we can set up our equilibrium expression like we see here. So this is AA on the left, products over reactants. So then we can cross multiply, divide by 0.1, and we're going to see in this case, X is going to be equal to 1.4 times 10 to the negative third. And if we go back, that represents X. So that's going to be the concentration of this fluoride ion. And then it's also going to be the change for these two. So it's going to be negative for the hydrofluoric acid. It's going to be positive for the hydronium ion. And in this question, we wanted the fluoride ion concentration. We also wanted the pH of it. So we just solved for X here. We just solved for the fluoride ion concentration. Now we can use this equilibrium concentration. With it, though, we don't want to just use this to calculate the pH. We want to think about the equilibrium. So it's going to be 0.1 plus that number. And really, it's not going to drastically change the pH. So if you think about it here, again, that's just the fluoride ion concentration for the hydronium, 0.1 plus that number, still essentially going to be the same thing because it's going to be 0.0014. So our hydronium ion would really be 0.1014. But based on sig figs, we're still going to have that same number. So when we take this and plug it into our pH equation, negative log of that concentration is just going to give us a pH of 1. So with it, the ice table is still relatively similar in terms of the calculation we're doing. It's just in this case, we've got a common ion present. So we're having the initial concentration already start with some of that hydrogen ion or the hydronium ion. Oops. Yeah. So let's see. Solve for this one. Okay, I'll do this one. So if you want to practice with this one, going to be kind of the same idea. So we're going to have to do our ice table. We've got a common ion with the NO2 minus, so that nitrite ion in potassium and nitrous acid, or potassium nitrite and nitrous acid. So with this one, get the pen working. But if you want to work through this one on your own, just pause it, or you can pause it at any point if you need a little help getting it started and then want to pause it, feel free to do that, or if you want to try it completely on your own. But just like the previous one, sorry, I'm not great at drawing with these styluses, with these mouse rather. Usually I use the tablet, the stylus, but this one I'm doing with the laptop. But we're going to have this dissociation reaction, because that nitrous acid is going to be a weak acid. So when we look at the initial concentration of HNO2, it's just going to be that 0.085. And in this case, we're not going to have any of the hydrogen ion initially, but we are going to have 0.10 molar of the nitrite ion. And then when we think about the change here, whoops, still going to be negative X for that reactant, positive X for each of the products. So when we look at the equilibrium concentrations, we're again going to be able to essentially ignore X for the reactant, as well as the product that already has some of that substance. So for the nitrite ion, we already have some of it present. So since this is going to be a reactant-favored reaction, 4.5 times 10 to the negative fourth, we're only going to have a little bit of it pushed to the right. So the negative X here really isn't going to change this value too much. The positive X, same thing for this one. So when we go through and set up our equilibrium expression, we'll be able to set Ka equal to 0.1x. Do that just a little bit neater. Let me make this decimal a little bit bigger. So 0.1x over 0.085. And then at this point, we can cross multiply. I didn't plug in what this number actually is, but we'd have 4.5 times 10 to the negative fourth here. So we could cross multiply that by either 0.085 divide by 0.1. And what we should see is x is going to be equal to 3.8 times 10 to the negative fourth. And again, we can see not really going to change these numbers at all when we subtract it from the reactant or add it to the product. So that's why we can essentially just ignore it, consider it to be negligible. But now that we do have the value there, that represents this hydrogen ion. We can use this, we can plug it into the pH is equal to the negative log of the concentration here. And what we're going to see is the pH. And we're going to want 2 digits after the decimal for the pH. Since we've got 2 sig figs here, remember with pH, the first number isn't really significant. It's just after the decimal. So what we're going to see in this case is we'll have a pH of 3.42. But again, still kind of the same idea in terms of this ice table. The only thing we're changing from sort of the previous one, and we saw it a little bit with the polyprotic acids. So if we looked at the second dissociation, we saw we already started with some of that H plus from the first one. And we're seeing kind of the same idea here with the ice tables. It's just one of those ions we've already got some amount of just because we're having that common ion effect. And with this, what we're going to see is the pH here. Since we're going to get less dissociation, the pH of the solution is going to be higher than it would be if we didn't have any of that potassium nitrate. Because this nitrate ion, this common ion, is decreasing the amount of ionization here. So it's decreasing the amount of H plus we actually produce. And with these equilibrium, one thing, I'll just write into the previous slide. What we're going to see is a very important type of solution is going to be a solution that has a weak conjugate acid-base pair. So if we think about, do either of these have actual names? None of these actually show what they are. But with these buffer solutions, they're going to have the conjugate acid-base pair, a weak conjugate acid-base pair. And what that's going to allow the solution to do is be extremely resistant to pH changes. So if we've got a buffered solution, we can add acid to it, and it will decrease the pH slightly, but it's going to be very minimal, at least to a point. Eventually, there's a what's known as a buffering capacity where it can no longer handle the addition of extra pH, so it would drop quickly. And the same thing with base, it's going to be resistant to that pH change, so it's going to rise very, very slightly. But for the most part, it's not really going to change at all. And the reason for it is because that conjugate acid-base pair, since we've got both of those pieces, the conjugate base is going to be able to sort of withstand the addition of acid. The conjugate acid is going to be able to withstand the addition of base. And that's why we're going to see these solutions aren't or are resistant to pH change. And with these ones, I should say this is very important environmentally. So if you think about something like acid rain, if the lake or the river that acid rain is being deposited into, if it's not a buffered solution, it's not going to be resistant to pH change. So just a small amount of acid rain can drastically decrease the pH of that water system. And that's going to have big impacts on the animals or the plant life in that area. Whereas if it is a buffered solution, it's going to be able to withstand that additional buffer, or the additional acid rather. And we're going to see that the pH won't really change at all. And then there's going to be other examples of buffered solutions, things like soda, your blood even is a buffered solution. And that's going to be important biologically just because if we think about the enzymes and things in your body, they're only going to work in specific conditions. So similar to why it's problematic if you get a extremely high temperature, it starts to denature enzymes and proteins and things like that. They just won't function properly. Same thing with pH. If you get outside of a certain pH range, just components in your body are just going to stop functioning how they should be. So if your pH or if your blood wasn't buffered, the pH of it could change drastically, and that's going to affect your body, of course. But with the buffers, the way they work, like I said, is they're going to have the conjugate acid-base pairs. So if we look at something like this, in the middle, we've got an equal amount of hydrofluoric acid, and then the fluoride ion is going to be its conjugate base. This could be present from the addition of something like sodium fluoride. So if we take hydrofluoric acid, if we take sodium fluoride and dissolve them in water, we can get equal amounts of these, and now we're going to have a buffered solution. So if we look at what happens when we add hydroxide, that hydrofluoric acid, that HF, we're essentially going to be able to kind of have a neutralization reaction occur, where with the addition of hydroxide, it's going to react with the hydrofluoric acid to just give us water and then more of that fluoride ion. It's going to help resist the pH changes by consuming some of that hydroxide. And then in the other case, if we add acid, so if we're adding H plus now, we've got that fluoride ion present. So what we're going to see is those are going to combine to just give us more of that hydrofluoric acid molecule. And again, it's going to be resistant to pH change because it's going to be removing that H plus from solution and just giving us the HF molecule. And with this, we're going to be able to do calculations with these buffers. So if we look at the reaction here, this is just a generic reaction where we've got HA as the acid, water is going to be serving as the base, and then we've got the conjugate acid hydronium on the right, conjugate base A minus on the left. So if we look at the acid dissociation constant, the expression for that, we're going to have hydronium times A minus on the top, and then on the bottom we can remove the water because it's a pure liquid and just have the HA on the bottom. We're then going to be able to take this equation and rearrange it a little bit. So if we kind of just pop the hydronium ion out in front, we can have hydronium times the conjugate base over the acid. And then if we take the negative log of everything, and again, this is equal to Ka initially. So if we take the negative log of everything, this piece, the H3O plus, is just going to be equal to the pH. This piece over here, we're basically just going to have the log of that. So we're not really going to change that too much. But the log of the Ka is just going to be known as what's known as pKa. So pKa is just going to be taking the negative log of that Ka value. And what we can then do is sort of rearrange this, make it a little bit nicer. So we can see pKa is equal to the pH minus the log of the base minus the acid. So again, we had A minus over HA, so that's why we just have base minus acid. And we can then further rearrange this into what's known as the Henderson-Hasselbalch equation by just having pH. So that's going to be the pH of the solution will be equal to the pKa, so the negative log of that Ka value, plus, because in this case we rearrange it, so that's why it's becoming plus here. It's essentially just subtracting it, or adding the log of this piece to both sides, plus the log of the base minus the acid. And with this, when the concentration of the base and the acid are the same, this is just going to be equal to 0. The log of 1 is just going to be 0. What we're going to see in that case is that the pH and the pKa are just going to be equal to one another. So when the base and the acid concentration, so when A minus and HA are equal, this whole term just becomes 0. So pH is going to be equal to the pKa. And if we look at this question, we're going to be using that sort of equation. We want to determine what the pH of a buffer that is 0.12 lactic acid. So it gives us the formula of lactic acid there, and 0.1 molar sodium lactate. And then we're given the Ka of that. So if we go back, we're looking for this. We're given the Ka, which is just going to be the negative log to get pKa. So we can solve for this already. We're looking for pH. And then with the log base over acid piece of it, since we're given the concentration of these two solutions, or two components, I guess, because they're going to be in the same solution, we're going to be able to solve for that piece as well. So ultimately, we'll be able to use all this information. We'll be able to use that equation to solve for the pH of this buffered solution. And when we do it, what we're going to be able to do is just plug in 0.1 molar on top, 0.12 molar on the bottom. And the reason for that is lactic acid is going to be our acid. This is going to be a weak acid. What we're going to see is very little of it's going to dissociate. So we're just going to be able to use this 0.12 to represent the concentration of HA. And then when we look at the second piece of it, when we look at the sodium lactate, it's going to be essentially the same formula. We're just going to have Na instead of hydrogen here out in front. But since we've got that group 1 alkali metal with it, we've got sodium, which is going to be super soluble with pretty much everything. We're going to see this piece is going to completely dissociate. So when we look at the concentration of just A minus, it's just going to be equal to this, because for every 1 molecule of sodium lactate, we're going to get one of these lactate ions. And we can just, again, plug all of that in. So A minus, the sodium lactate, or the lactate ion, is 0.1. The lactic acid is going to just be that original concentration, because very little of it's going to dissociate. And then pKa here, again, is just the negative log of Ka, which we were given. So it's just basically plugging all that in, doing the calculation. And what we're going to see here is the pH is going to be 3.77 when we ultimately go through and solve this one. And then these are just some general points related to buffer solutions and choosing the correct buffer. Generally, you want to have the pKa of whatever that acid's going to be. You want it close to the pH that you're trying to reach. All right, but looking at the one we have here, I think I have. I go through and actually. Yep. All right. So for this one, we want to figure out how much ammonium chloride we're going to need to add to 2 liters of a 0.1 molar ammonia solution in order to make a buffer that has a pH of 9. And what we're going to do is assume that the ammonium chloride isn't going to affect the volume at all. So we're going to kind of assume that the 2 liters just won't change with the addition of the ammonium chloride. And with this one, what we need to do is have a little bit of information. So we'll have pH is equal to pKa plus log A minus over HA. So if we're looking at what we have here, we want a pH of 9. The pKa is just going to be based on the ammonium ion. So NH4, we would need some information about this. But for NH4, Ka is going to be equal to 5.6 times 10 to the negative 10th. So with it, we can then solve for pKa by just taking the negative log of that value. And then for the rest of this, if we look at the solution, we've got HA, or excuse me, we've got A minus. Because if we think about the reaction that's going to occur here, so the base, I really should have wrote base over acid here. So I just change that. There's the eraser on this thing. There we go. So if we change this just to make it a little bit easier, a little bit more coherent for this question. Whoops, I got real messed up. But again, it's going to be base. Ooh, struggling to write words with this. Over acid. And again, the ammonia here is going to be that base, so we're going to have 0.1 on top. We're trying to figure out what the concentration of this needs to be. So if we go through and get rid of all of this. What we're going to have here is pH of 9.00 is equal to the negative log. And then I'm just going to write Ka, just so I don't have to write as much with this mouse, just because I'm not very good at it. But that's just going to be the 5.6 times 10 to the negative second. So when you plug that in, what we're going to see here is this term should just be equal to 9.25. But then for the log base, we'll have 0.10 just for the ammonium, or ammonia rather, over X for the ammonium ion at NH4 plus. And when we go through, like I said, this term becomes 9.25. So we get negative 0.25 is equal to this piece. And you can then just go through, do the algebra, raise both sides to the power of 10. So we'll have 10 to the negative 0.25, 10 to the log 0.1 over X. And what we're going to see when we do that is X is going to be equal to 0.18 molar. For this one, though, we don't want the concentration of the acid at that in order to get this pH. We want to figure out how many moles of ammonium chloride were needed. And for this solution, since it's 2 liters total, moles per liter, we've got 2 liters. We're essentially going to double this. So we're going to see we're going to need 0.36 moles of NH4 plus, or of NH4Cl, however you want to think about it. It's going to be the same. But again, with this one, this is the concentration. We're looking at how many moles. And since we've got 2 liters, this capital M is moles per liter. We would have twice as many moles in the solution as we would in 1 liter. That's why we can just double it here to get the 0.36. And with this one, another way you could do it is there's a similar equation. pH will be equal to, or POH will be equal to pKb plus log of acid over base. So we could have done 5 is equal to the Kb, or negative log Kb for ammonium, and then just have this piece basically switched. But we're just going to look at the Henderson-Hasselbalch equation in terms of the acid, in terms of pKa, like we have here. But if we were given Kb for ammonia, excuse me, I keep saying ammonium. But if we were given the Kb for ammonia, we could solve for Ka just by using the water solubility, Kw, or water dissociation, water ionization, whatever you want to call it, Kw, in order to solve for Kb, Ka, just using that relationship. Let me clear this out. Okay. But looking at these ones, when we have a buffered solution and we add a strong acid or a strong base to it, essentially what we can do is assume that all of that strong acid or base has reacted. So if we look at it, in this case, we've got our buffer solution contains the acid and the conjugate base, so X minus. If we add a strong acid to it, it's going to the acid itself is going to dissociate. So we'll get the hydronium or the H plus. But when we have those react, what we're going to do is form more of the weak acid. And then with the addition of the strong base, we'll kind of have the opposite occur. In this case, we're going to have the hydroxide ion being added. So we're going to have that react with the weak acid. And it's going to cause some of that weak acid to essentially dissociate. We'll have that H plus neutralize the hydroxide, and we'll just get X minus. So if we look at it, the reason we're not seeing the pH change drastically here is because we're just using the conjugate base. We're using the weak acid in order to essentially neutralize whatever we're adding. So it immediately basically gets neutralized. It does change the pH slightly, but for the most part, nothing really changes too much about the pH until we just run out of the buffer. But at least initially, we can just have either the strong acid or the strong base just get neutralized. And when we do that, what we're going to see is we've got to change the concentration of the conjugate acid base. So for the addition of a strong acid, we're converting that conjugate base into the weak acid. So we're going to see if we added 0.2 molar strong acid, we're going to use up 0.2 molar X minus. We're going to use up 0.2 molar of the weak base, or the conjugate base rather. And we're going to increase the conjugate or the concentration of that weak acid by just as much. And conversely, with the addition of the strong acid, we see just the opposite. We're going to use up some of that weak acid, and we're going to produce some of that conjugate base. And then, of course, we can then use that, figure out our other pieces just to get the overall pH. Okay, so with this one, if we've got a buffered solution, so in this case, let's say we took equal moles of acetic acid and then sodium acetate and dissolve them, so we've got 0.3 molar of each of them. What we're going to see is when we add hydroxide ion, this bottom one, if it's sodium hydroxide, we'd see the increase, I guess, in sodium acetate. But the bottom one here really should just be the acetate ion rather than sodium acetate. But what we're going to see is with the addition of hydroxide, that OH minus is going to react with this weak base. And if it's 0.02 mole, we'll see, assuming that this is 1 liter of solution, we'll see the concentration of that weak acid is going to decrease by just as much, while the concentration of the conjugate base, that acetate ion, is going to increase by that same amount. And then conversely, and if we think about it, we're adding OH minus, we're removing some of the weak acid. So that's why the pH is going to increase slightly here. But again, you see it doesn't change drastically because it's a buffered solution. It's going to be fairly resistant to that pH change. So it only goes up by 0.06. If we added 0.02 moles of hydroxide to pure water, we're going to see that pH is going to skyrocket immediately. And then with the opposite, with the addition of hydrogen ions, now what we're going to see is that's going to react with the acetate from sodium acetate to give us more of that weak acid. And we're going to see, because of that, we're going to decrease the concentration of that acetate ion. And that's why we see here the pH decreases slightly in that case. So if we wanted to see the actual calculation here, a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. The pH of this buffer, after mixing those together, is going to be 4.74. We want to calculate the pH of the solution after 0.02 moles of sodium hydroxide has been added. So with this one, initially, since we had 0.3 moles of each of those, the moles of acetic acid and the moles of that acetate ion are going to be the same. So if we think about the Henderson-Hasselbalch equation, the second piece of the right-hand side, that log base over acid, is just going to be equal to 0. So what we're going to see is the pH is equal to the pKa. That's where we got the 4.74 initially, just taking the negative log of that Ka for acetic acid. 4.74. But with this one now, we're taking that buffered solution and adding sodium hydroxide to it. So before the reaction, you can kind of think about these two here. We don't really have that present before the reaction technically, but or at least we don't have it in the same solution. But again, we had 0.3 moles of each of those, 0.3 molar, if you want to think about it that way, since this is a 1 liter solution for this one. But now when we add the hydroxide to it, we have this reaction occur. We have the hydroxide react with this weak acid, essentially causes it to dissociate so that hydrogen can neutralize the hydroxide. That's why we just wind up with water here. But it's also going to then increase the acetate ion concentration. So that's why we see the acetic acid decrease by 0.02, whereas the acetate ion increases by 0.02. And again, like I mentioned earlier on that picture where it was listed as sodium acetate, we're really just focused on the acetate ion itself. We're not really too concerned with the sodium portion of it. But now that we have the concentrations of these after the reaction, we can use these in our Henderson-Hasselbalch equation. So again, 4.74 is just that pKa, so that's why we have this value already. But plug plus the log of the base minus the acid, so we increase the concentration of that acetate ion, that conjugate base. We decrease the concentration of the acid, so that's why we have 0.32 over 0.28. And what we're going to see here is, let me just double check to make sure that's correct. Log 0.3228. Yep, so 0.06. And then when we just add those together, we get 4.80 there. And with this, it makes sense that the pH went up slightly, because again, we're adding that hydroxide, so we're neutralizing some of that weak acid. We should see the pH increase slightly. And then with this, we'll stop here for this first video of chapter 17, but with the next ones, we'll kind of continue to see some of the similar stuff, but we'll be focused on specifically titrations there.